Welcome to a lesson with Dr. Powell. Let's look at an example of Lagrange multipliers. Let's try to find the minimum distance that there is from the plane and where it occurs. From the plane z squared is equal to xy plus 4. In order to do that, what we're doing is we're trying to minimize a distance. So the square of the distance from the origin of the point xyz is simply x squared plus y squared plus z squared. So we just try to minimize this. And this is our constraint function. So what we need is that the gradient of f is parallel to the gradient of the constraint, which is thought of as a level surface to a function with 3 inputs. So we're going to take the gradient of this and the gradient of this, and they need to be parallel to each other. So we take the gradient of f, 2x, 2y, 2z, and that needs to be parallel. So we have a constant multiplier lambda multiplied by the gradient of g, which is yx negative 2z. So we get 3 equations here, and we have an equation here when this is set equal to 0. Since right here, if we subtract z squared over, that's going to be, this equation is equal to 0. So that means it's going to be the level surface of this function, which means it's all of the input values that make the output value of 0 for g. So this right here is our 4th equation. So we have 4 equations and 4 unknowns. Okay, so these equations right here, thinking component-wise, are 2x is equal to lambda y, 2y is equal to lambda x, and 2z is equal to lambda times negative 2z. Okay, notice first of all, if z is not 0, then, so we'll take a case, when z is not 0, then what happens? Then lambda must be negative 1 when we divide this negative 2z over. Lambda is equal to negative 1. Okay, now if lambda is equal to negative 1, then what does that mean? That means that 2x is equal to negative y, and 2y is equal to negative x. Well, notice here, since y is equal to negative 2x, you could plug that in here. We get 2 times negative 2x is equal to negative x. So this ends up being negative 4x is equal to negative x. Now, if we were able to divide by x, this would be a false statement, like negative 4 is equal to negative 1, which is false. You can't have that. Well, that actually means that forces that x must be 0 in order for this to be true. And notice, if x is 0, then y must also be 0. So, in the case that z is not 0, then we force x and y to be 0, so we get a point, 0, 0. How do we find this? Well, you just plug it in here, 0, so 4 minus z squared is equal to 0, which requires that z is plus or minus 2. So we actually get these points right over here from the case when z is not 0. Let's look now at the case when z is 0. When z is equal to 0, then in this equation we have xy plus 4 is 0, or in other words, x times y is equal to negative 4. Now let's use this idea. Take this equation right here and multiply it by y. If you did that, we'd end up getting 2xy is equal to lambda y squared. Now, why did we do that? Because I noticed this chunk I would get would be this right here, a negative 4. So I'd have a negative 8 is equal to lambda y squared. But here I multiply both sides by x to get a 2yx. So basically I get negative 8 again over on this side. Multiplied everything by x, so this would be equal to lambda x squared. Well, this means that these two things right here are equal to each other. Notice this is perfectly fine because lambda could be negative in this case. Well, we also know that xy is equal to negative 4, and we know that x squared is equal to y squared. These two conditions alone tell us that we get 2 solutions from this in x and y. We either get 2, negative 2, or we get negative 2, 2. And notice that we've required that z was 0. So we end up getting 4 potential points to check for the minimum. So if we put these in, obviously these points right here give us a minimum value for this, a minimum of 4 for the output of f, which would be, if you take the square root of that, it would be 2. So a minimum distance of 2. And it occurs at these points right here. Thanks for watching.